It might help if I turn the mute on, or the mute function. Oh, there we go. So the video didn't record the last minute of things I was saying because I forgot to turn the mute off. That's great. Whoops. So we're talking about stress analysis and looking at an eigenvalue approach to assess principal stresses and what have you. We did a little bit of this last time. We looked at a stress state and we said, all right, we can look at this from a Mohr circle approach, and what you're calculating is essentially the center plus or minus the radius to get sigma 1 and sigma 2. And we go through that calc. And we say, all right, I can write a stress tensor for this approach, 2 by 2 since we're dealing in 2 dimensions. Look at it from an eigenvalue problem, get a quadratic equation, solve the roots of that quadratic. Lo and behold, we get the same answer. So this eigenvalue approach has some significant benefits in 2 dimensions, but not only that, in 3 dimensions as well. Now, in 3 dimensions, we're dealing with a stress tensor that looks something about like that. Again, 6 unique terms because it's symmetric. It's the same problem, eigenvalue approach. And we say, all right, we can simplify that out a little bit using these stress invariants, I1, I2, and I3, for our regular stress tensor. Once we get our principal stresses, once we get our principal stresses, if all we care about is calculating our invariants, it's actually pretty simple. We take I1 as just summing them up, I3 is multiplying them out, and I2 is sort of this mixed sum product approach as you see here. It's pretty straightforward. Now, as we talked about last time, it's also important for a lot of materials to subtract out that hydrostatic stress component. So we develop a deviatoric or a deviator stress tensor. We call that Sij. If you do the same approach, you can get an S1, an S2, and an S3 and do the same thing. Or using the deviator approach, you can use the same concepts to get a J2 and a J3. By default, J1 is 0. Lastly, if you cut a plane and you want to stress on some random plane, it's just a dot product, your stress tensor times your vector, and keep in mind it has to be a unit normal vector. Lastly, to get the normal component dotted again, the shear component, it's sort of a blown up Pythagorean theorem is basically what it is. All right? Whoops, that's a typo. Those need to be squared. Sorry about that. This txy, or tx squared, ty squared, tz squared, those need to be squared. I'll fix that in a subsequent set of slides. Okay, we started this example, but we didn't finish it, right? Because we got our principal stresses, but we didn't do any of this. It's actually really simple, okay? And I want to walk through that. I'm going to bring up the smart board to do this right here. So let me put eigenvalue example. Okay, now what we got last time was a sigma 1 of positive 50, wasn't it? Sigma 2 was positive 20, and sigma 3 was minus 50. Was that right? Is that what we got last time? Let's see. Yeah. 50, 20, and minus 50. Usually when you write principal stresses, you go in descending order. Sigma 1 is your largest value. Sigma 3 is your smallest, and ranked accordingly. All right, let me set this over here. Get my screen situated where I can actually do a little bit of writing. Okay. If you want to calculate your stress invariance, it's pretty easy. All right, so I1 is literally sigma 1 plus sigma 2 plus sigma 3. So that's going to be 50 plus 20 minus 50, which is 20. I2 is this mixed product approach, sigma 1, sigma 2, plus sigma 1, sigma 3, plus sigma 2, sigma 3, which is 50 times 20 plus 50 times minus 50 plus 20 times minus 50. And you do the math, and that comes out to be negative 2,500, and that's okay, especially for your I2 and I3. They can come out negative. That's no big deal. I3 is just sigma 1, sigma 2, sigma 3, which is, if I do it in correct order, 50, 20, minus 50, and that is negative 50,000. Okay? Now, J1 for any stress tensor anywhere is always 0. Okay? Because remember, when you do your deviatoric stress tensor, you're subtracting that sigma average along the main diagonal, so you're subtracting it 3 times. And you're subtracting the average over 3. So you're basically taking sigma x plus sigma y plus sigma z minus sigma x plus sigma y plus sigma z. So it's 0. It's always 0. Now, using this data, the easiest way to calculate J2 and J3, J2 is just 1/3 I1 squared minus I2, which is 1/3 of 20 squared minus a negative 2,500, which is 2633. And J3 is just, it's a little more involved. 2 over 27 I1 cubed minus 1/3 I1 I2 plus I3. I'm going a little fast, I think, but this is really plug and chug, I would imagine, right? So 2 over 27 times 20 cubed minus 1/3 times 20 minus 2,500 plus, I guess if I wanted, I can just distribute that out and say minus 50,000. Plug and chug, and that's negative 32,740.7. That's close enough. Now, is everybody all right with that? So I got to believe that the invariants are simple. Once you get your principal stresses, it's about as plug and chug as it can get. Now, what comes next? There's a little bit of thought that goes into that. Okay, I'm gonna bring it back to statics. Do you all need me to leave this up for a second, or are you good? Okay. Now, let me go back to the slideshow to make sure everybody's remembering what this last part is. So, I want to determine the stress on the plane defined by the following vector. Now, remember, how do you define a plane in statics or in mathematics using vectors? The plane, or the vector, is the normal vector to that plane, right? You have a vector, everything normal to that is your plane, right? But what we need is a unit vector, okay? So let's go back to vectors. I know it's been a while since you might have looked at it from this approach, but not too bad. Okay, so I'm going to put stress on a plane as opposed to snakes. No, come on. All right, that's our plane. Our plane is defined by the following vector. And this is going to sound silly, but I'm doing this for a reason. Would a fair way of writing this be 1i plus 1j plus 1k? Is that a fair statement? All right, the reason why I'm doing that is How do you determine the magnitude of a vector or the length of a vector? There you go. We're gonna use Pythagorean theorem, just expanded to 3 dimensions. So the we'll call it the magnitude is the square root of 1 squared plus 1 squared plus 1 squared. And I'm getting that by saying, you know, that one is here, that one is here, and that one is here, right? Now, if you do that, you're going to get the square root of 3, right? So I propose to you that a unit normal vector is 1 over the square root of 3i plus 1 over the square root of 3j plus 1 over the square root of 3k. I divide each of those terms by the magnitude or by the length, because if I calculate the magnitude of n, I'm going to get 1, a unit vector. Okay? Make sense? So if you want, you can say your stress vector equals the original matrix. What is it? It's like 20, 0, 0, 0, 30, 40, 0, 40, minus 30, and then 1 over the square root of 3. 1 over the square root of 3. 1 over the square root of 3. I have got to believe by now that you can do that in Microsoft Excel. You can matrix A times matrix B. You do that and you'll get the following: 11.547, 40.415, 5.774. So those are the stresses on that plane, okay? So the idea is this, okay? I have this element, if I'm doing analysis of a V8 engine or a, you know, cable-stayed bridge or some complex problem, and at some point I've got a stress state defined by this. And I want to know what the stresses are in that direction, you know, I plus J plus K. Cut a section, these are the stresses I'm going to get in the X, Y, and Z. Now, if I'm an engineer, maybe all I care about is normal stresses and shear stresses. To get the normal stress, what I do is I take T and I dot it with N. Now, how do you do a dot product? Number times number, right? So it would be 11.547 times 1 over the square root of 3 plus 40.415 times 1 over the square root of 3 plus 5.774, 1 over the square root of 3. Do that and you get a normal stress of 33.33. And that would be, I guess, what, KSI? If this problem was originally in KSI. And then your shear stress would be so plug and check that out and you're going to get about 26.25. What do you think? Turn that off. All right. Any questions? Any questions? All right. If that's the case, I have an assignment for you. It's on the Blackboard course content page as well. I realized that I hadn't given you all a numerical integration problem as well, so let me pull that up. Don't worry, it's not a full-blown, element calc like what we did that one time. Just to kind of give you an overview, I'll pull it up. So, I really believe that this is a short assignment. I just wanted to do it just to say that we had gone through the process. But problem 1, utilizing Gaussian quadrature, I want you to integrate this, okay? Using 1-point integration and 3-point integration, plus you all are seniors or graduates with a bachelor's degree, you should be able to compute percent error. So you're going to get an answer for percent error with 1-point integration. You're going to get an answer with 3-point integration. I want you to compare it against the actual answer, which you should be able to integrate that. If not, how many different online tools are there to do integration? So that's pretty simple. Problem number 2, I gave you a stress tensor, and I want you to do kind of the same thing. All right. Simple stuff? Everybody good? Okay. Now, if that's the case, I do want to move into our, does anybody need this stuff? Next Tuesday. But it's short, so. Does anybody need this stuff on the board? Okay. I'm not going to worry about saving that. All right. I want to talk about vibration, or mechanical engineers will call it vibrations. Civil engineers will call it structural dynamics. It's the same thing. Okay. So let me get this passed out. Hold on. Give me one moment. If you don't have the analysis of stress and strain handout, I've got some up here. I'll get them here in a little bit, or once class is over, you can come up and grab one. All right. So I got a number of you all that are in advanced vibrations right now, so you're probably going to sleep through some of this, and that's fine. But what I want to do is I want to show you all one of 2 very critical classes of finite element problems that involve eigenvalues. Okay? One of them is a vibration analysis. In other words, determining natural frequencies. My vibration folks should know what I mean by that. The second is a buckling problem, which between the 2 of those, they're pretty much the crux of the matter. What the heck? Did my slides not save? Oh, I'm going to be upset if my slides didn't save. Well, that's the case. We'll go off the handout, because I do that for a reason. Luckily, I have a hard copy saved on a flash drive. So, oh well, we'll just go with this. Okay, so up until now, what we've been doing in this class are problems like this. Okay, and what I mean by that is that we have only been considering our response as a function of the applied loads, and really that's it. Okay? Now, a simple way of explaining how sometimes this isn't, or can be a problem, is let's take one of these computer desks. I mean, these are fairly new computer desks. I think they're fairly sturdy, but I'm I would like to think I'm not a complete idiot. Let me ask you this. If I had to guess, they could probably support my weight. Okay? But what if I jumped on them? You know what I mean? And applied my load suddenly. Okay? Would it stand to reason that there'd be a stronger force effect being applied to those tables if I jump on it opposed to if I just sit down? Now don't get me wrong, assuming everything behaves linearly and behaves elastically, when all the smoke settles, the force effect should be the same. But if you consider time to be a variable, then that's going to be cause for concern. Okay. What you can find, and this is really why structural dynamics and vibrations are even a field of study, is that if you consider time, you can actually have a worse effect than if you assume everything's applied statically. In other words, if I take a load and just set it on the table versus slamming it on the table, you can have a more pronounced effect. That's why we study structural dynamics. That's why we study vibrations. Now, one of the things I want to do is kind of go through, if you will, some of the math and some of the issues associated with this. So what I want to do, this slide is just for notation purposes. I want to consider displacement, instead of just being a function of just a scalar value, I now want to look at it as if it's a function of time. Okay? Now, if you take a course in structural dynamics or advanced vibrations, usually what you do is if you take derivatives with respect to x, you use prime, like u prime, u double prime. If you take derivatives with respect to time, or with respect to t, use dots. So u dot, u double dot, and what have you. So I'll use that notation in here as well. So u dot would be the derivative of position with respect to time, and we call that velocity. U double dot is the second derivative with respect to time. We call that acceleration, right? So Newton's second law tells us that force is proportional to mass and acceleration, or force equals mass times acceleration, or mass times the second derivative of deflection. Make sense? So if that's the case, I can idealize a system now to look something like this. I mean, before we were looking at spring systems, right? Force and equals stiffness times displacement, and we represented stiffness as if it was a spring. Remember that? Now that spring could be the stiffness could be AE over L or whatever, but in the end this is really what we were talking about. Now I propose to you that there's another variable that we need to assess. It's mass. Okay? I propose to you that when we apply loads and we consider time to be a factor, because of Newton's second law, it's not just stiffness that is resisting those loads, it is the system's own inertia. Okay? So the equation is not just Ku equals the load, it's Ku plus mass times acceleration equals the load, and we get this. Okay? Now my structure, or my advanced vibrations folks, are probably wondering, where's the dash pot? Where's the damper? The Cu dot. We'll get to that. We're actually not going to consider that in this course because this isn't advanced vibrations, but we'll talk about it. Okay? And this is really more meant to sort of open your eyes and give you some additional tools under your belt. Now, for this system, we're only considering the movement of a single point. Okay? The single point either moving in the x direction with respect to time. We call this a single degree of freedom system. When you take a course in vibrations, you'll learn about single degree of freedom systems first, and then you explore those and hammer those into the ground, and then you say, okay, what about a multi-degree of freedom system? Which we've been talking about multi-degree of freedom systems in this course like all semester. That's what we've been doing. Okay? Everybody good? Okay. Now, the easiest way, or the easiest case to consider is to start off, let's look at a system that is undamped, and let's also look at a system that has no load on it. In other words, the load equals 0. And you go, well, when the heck does that ever happen? That is a case of free vibration. It happens all the time. Think about a guitar. I take the guitar, I pluck the string, I let it go. What does that guitar string do? It goes, boom, it makes a sound, right? It makes a sound because it is vibrating, okay? but there's no applied load. Okay? It is undergoing free vibration. Okay? Now, I introduced to you now a term, and I'm calling this term omega. Omega stands for the, and this won't make a lot of sense now, but it will here in a little bit. I propose to you that omega is the system's natural frequency, but it's circular natural frequency. There's a difference between its circular natural frequency and its cyclic natural frequency, and it's just 2 pi, okay? And you'll see where we get that here in a little bit. Okay? So if I look at my system, I say, all right, mu double dot plus ku. I divide m on both sides. Over here it's just 0. This k over m, I'm calling this omega squared, and I get this. So now I have a second order differential equation. Now, first off, you all should know how to solve differential equations, I would hope. But if not, let it be said that I know things about stuff. See, what is it? Was it Wolfram alpha? Is that what it is? Yo, you don't know? You don't know? Oh, never use this, right? Don't. Well, watch this. Okay. For the purposes of using Wolfram alpha, I'm just going to use like conventional notation like primes and y's and x's. But really what we have is y double prime plus, we'll call it a squared, and see there it is right there. A squared times y is a familiar differential equation. I mean, I know it's in primes in terms of dots, but in the end it's the same concept. And in the end, it identifies it as a second order linear ODE, ordinary differential equation. And in the end, it provides the solution. So you all, if you want, you can write the characteristic equation, recognize that you've got imaginary roots, and imaginary roots yield sines and cosines. Or you can use, I don't care. This isn't differential equations. So, but in the end, you're going to have, C1 times the sine or C2 times the cosine, arbitrary constants times your trig functions. Make sense? So I propose to you that the solution to this differential equation is as follows. That u equals C1 times the cosine plus C2 times the sine, and it's the sine of omega times t. Make sense? Okay. All right. Now, to solve for our unknown constant, we're going to employ boundary conditions or initial conditions. I guess I should be a little more clear about that. I guess technically these are initial conditions. Usually in these types of physics-based problems, initial conditions are conditions at t equals 0, or a function of time, and boundary conditions are your x dimensions, your physical boundary conditions. So we're dealing with initial conditions now. So I propose that we have 2 boundary conditions. Think about the guitar string. I take the guitar string and pluck it. I propose that when you're dealing with free vibration, you at most have an initial displacement and an initial velocity, right? Think about what happens in the guitar string example. You take the guitar string, you pull it up, and let it go. But that very notion, now if we're talking about that instance, I would argue it has an initial displacement. It does have an initial velocity, but it's probably 0. Because I'm just pulling it and letting it go. Make sense? But if I pull it and maybe, I don't know, give it a push, then it's got an initial velocity and position. Make sense? So take the first one. The initial condition is that the displacement at time equals 0 equals u naught. So here's my displacement function. Plug in t equals 0. What's the cosine of 0? 1. The sine of 0, 0. So this gives me that my first constant is u naught. Do the second thing for the derivative. I've got to take the derivative of this function. So what's the derivative of the cosine? The negative sine, right? Chain rule tells me I've got to stick an omega out here. Same thing over here. Derivative of the sine, positive cosines. That's where that negative comes in. All right? Plug in u naught, plug and chug, and here's my second constant. Okay? Now, what that tells me is that this equation models what the vibratory response of a single degree of freedom system is that's under free vibration with no damping. Okay? I propose that with no damping, it will just continue to vibrate on forever. That vibration is defined by its initial displacement, which is some value on the y-axis here, and some initial velocity, which, keep in mind, this function is its displacement. Okay? So the slope of that function is its velocity, right? So some displacement and some velocity will define what this looks like. Okay? Now, what about its period? Okay? In other words, how many waves you get in a single second, or how long it takes to go through a complete cycle of vibration. Those are functions of the system itself. Its mass, its stiffness, what have you. Make sense? Okay. All right. So a few notes. Okay. As I said before, omega is your circular natural frequency. F is your cyclic natural frequency. It's so if we're talking about circular natural frequency, we're talking about radians per second. Cyclic, we're talking about units per second, or hertz. You all heard hertz. So if I take this table and I bang on it, how many vibrations am I going to get per second? It's measured in hertz. So its period is just 1 over that. Okay? Make sense? Okay. Now, if we're talking about units, this is just so you all know, I deal in American or USCS units. So displacement, if it's in inches, your velocity, let's say inches per second squared for acceleration. Stiffness is always kips per inch. Mass, this might seem a little iffy, but what I'm doing here is I'm taking unit weight, kips per cubic inch, and I'm dividing it by acceleration. All right? How do you calculate a density? You take a unit weight and you divide it by gravity, right? Gravity, inches per second squared, or unit weight and kips per cubic inch. So this is your resulting units in USCS units. I know it's a little weird for mass, but it just is what it is. Okay? I would argue that this is probably one of the downfalls of US units. I get it. In SI, it would come out in some term of kilograms or grams or what have you, and it would make a little more sense. All right. Make sense? Okay. Now, in the real world, however, and my vibration students, could talk about this all night, but it ain't that simple in the real world. What I'm going to do with you all in this course is provide you just a general understanding of dynamic analysis, and it's really only with one application, finding the natural frequency. Beyond that, go ask Dr. Chen. He can tell you all about that. Okay? But I do want to at least expose you to some of these concepts. All right? In the real world, it's not that simple. Okay? Free vibration will always occur once the structure's loading has completed. It will undergo some free vibration. I mean, if I take this table and I kick it, you could almost idealize that as a sudden impulse load. But when it's all said and done, once my foot has left the table and it's done, it's now undergoing free vibration. So free vibration is always where you start when you do dynamic analysis, when you take the course, because every structure will deal with that at some point or another. Okay? Now, one other complicated issue is the concept of damping. Take a guitar, pluck the string. What happens after 10, 20 seconds? It dies out, right? Really, vibration doesn't just go on forever. It kind of just, like if I take a guitar string and pluck it, it'll go, and then it'll kind of die out. It's because that vibratory motion is dying out over a given period of time. It almost really looks something like this, okay? In other words, that over time, those oscillatory waves, the amplification just decreases. And if this were to stretch out to infinity, theoretically, it wouldn't move at all, okay? That's what's really going on. That's a little bit more of a realistic approach. Now, that comes from a number of different factors. Friction causes that effect. Air drag causes that effect, a number of that. That effect is what we call damping in the world of vibrations. And what we do mathematically, because it seems to make sense from a from a philosophical standpoint, we have a term related to displacement, its stiffness. We have a term related to its acceleration, that's its mass. What's left? Its velocity. So we introduce a proportional damping constant that we call C, and that is what we use to help or to express that other effect. I would argue that one of the most challenging aspects in all of structural dynamics is quantifying C. Okay? It's pretty easy to compute mass. It's pretty easy to compute stiffness. But C, by its very nature, is trying to represent all that other stuff that is hard to quantify. You know, how do you quantify all of the friction in a 100-story building? Good luck. You know, good luck with that. So yeah. Now, again, if you do have a system that is damped, and I could go on with this, there's 3 classes of damping. You have critical damping, overdamped, and underdamped. This is an underdamped system, which is the most common. If you have a system that is damped, it will affect your response. Again, go back to that guitar string. Take that guitar string, pluck it, it will die out over time. Okay? This is what happens to a damped system. This is probably like a damping ratio of 5%, 10%, something like that. Okay? One other complication is the loading itself. And my vibrations folks will tell you all about that, is when you're dealing with loadings that aren't zero, the math gets more complicated. If I have some random loading function, I have to handle what does the system respond, you know, during the load and then after the load. After the load, it's free vibration and we're good to go. But before that, we have this forced response, and that gets kind of tough, being able to superimpose those and make sure you get all the math right. Yeah, that can get kind of frustrating the first time you do it. Okay? And you can find some interesting effects. Y'all seen this curve, right? In advanced vibrations, I bet. Okay? For those of you that aren't in advanced vibrations, I'll tell you a little bit about this. So, would it be a fair statement that a lot of the stuff that we're doing right now deals with a lot of trig functions, a lot of sines and cosines? One of the first types of loads that you consider are harmonic loadings when you take that course. In other words, imagine that I took a structure and I went like this. And I assumed that that loading function was trigonometric in nature, a sine function or a cosine function or what have you, right? If I do that, I have now 2 things to consider. The actual frequency of the structure and the frequency of the loads, okay? Now this plot is a very famous plot in the world of structural dynamics, and what this does is it tells you how do structures respond when you start comparing the natural frequency to the loading frequency. Now, if they look what you're seeing, and you don't really need to like be an expert in structural dynamics to understand this, but what you're seeing on this curve is on the x-axis, this is the ratio of the structure's natural frequency to the loading frequency. So this value of 1 is when you're loading it at the frequency that it will respond to. And this is the response. Look how it just sort of shoots through the roof, okay? That's called resonance, okay? Everybody in here, I'm almost positive, has seen that classic image of the guy or the girl singing, and there's the wine glass, and they sing, and they hit that note, and the wine glass cracks, right? Y'all have seen that, right? That is an example of resonance. That wine glass, if I take that wine glass and I click it on the table and it undergoes free vibration, it has that ding, it has that sound to it. It has a certain frequency associated with it. If you produce an auditory vibratory wave onto that glass and match the frequency of the glass's deflection will shoot through the roof. It has no stiffness to resist those loads, and it'll shatter. Okay? That's what's happening. That's what resonance is. Okay? Everybody's seen that before, right? Make sense? Okay, so just you know, some larger issues so that you all know what's going on. Okay? Does anybody have any questions? Now, again, this is not a vibrations class, so, you know, Go ask Dr. Chen about steady state and transient analysis and linear acceleration procedures and all that, and step analysis and all that. But yeah, make sense? Now let's talk about the finite element approach and how that works. So what we do in finite element analysis is we don't really deal with many single degree of freedom systems. That would be a boring class if that's all we did in here. We deal with multi-degree of freedom systems, MDOFs. Okay? We can take a finite element approach to that problem as well. Okay? We choose an element type, we derive our N matrices and B matrices, and we equate the energies, the law of conservation of energy, to develop our finite element matrices. Same process as what we did before. Okay? So ultimately, again, we're going to stick to only undamped analyses and free vibration. What I want to do is get to this formulation and see how can we use finite elements to get to this. Okay? So the question is, we have developed a stiffness matrix before. We've done this. Now I want to talk about how do we derive a mass matrix. Okay? It's actually pretty simple, and I'm going to give you the ones for the bar and beam when this is all said and done. Okay? It's pretty simple. But the same process applies. Okay? Now I want to go back to a couple things that we did last time so that you're all aware of what's going on. So how did we go about finite elements originally? We actually started breaking it down, and we said, how are we going to derive a stiffness matrix? And we said, let's look at the law of conservation of energy. Energy going in has to equal energy going out. What about stored strain energy? We said we take the strain times the stress, we integrate it over the volume, right? Then we said we used our shape functions, our B matrices and what have you, to expand this into the following form. Make sense? Now, that's stored strain energy, okay? However, we're talking about a system that is undergoing free vibration. In free vibration problems, what is the external work done? There is no work done on the outside. So, therefore, right now, this is my expression, that the stored strain energy has to be 0. That doesn't make a lot of sense. We're missing something. Something's not right. And that is correct. There is something missing. The answer is the kinetic energy. Remember physics, 1/2 mv squared? Remember that? Okay. We need to throw the kinetic energy into the mix. Okay. So I propose that, if you recall from physics, okay, that the kinetic energy is 1/2 mv squared. If I want to tackle this from a finite element approach, I need to say, all right, it's 1/2, and then integrate that over the volume. So what I'm doing here is from here to here, I'm integrating over the volume. So you see I've got this rho term. That's the density, okay? Because if I integrate the density over the volume, that's where I'm going to get the total mass of the system, right? Now, I can't really square a vector, but what I can do is multiply the transpose times itself. Now I'm going to take each of those terms and square them up. Make sense? Now, I will admit to you, to be perfectly honest, I'm doing a little bit of hocus-pocus mathematics behind the scene to get from here to here. And the reason why is this isn't a vibrations course, and I don't want to get into that. You'll talk about Hamilton's principle or Lagrange's equation? Not yet. Okay, you'll talk about that at some point. Okay, this is what this arises from is using an energy-based approach to do structural dynamics. You're probably just solving the diffie-q's directly and doing that. And that's how you learn. That's what you do first. And then you go back and say, well, what about an energy approach? Using an energy approach, we can do the same thing. But the sort of hocus-pocus that I'm doing behind the scenes is I've got velocity times velocity, and here I've got displacement times acceleration. Now, I'll admit, I'm doing some stuff behind the scenes, but that's, again, because this isn't a vibrations course. Okay, does that make sense? But again, notice the vanishing 1/2. Remember that? Remember that 1/2 just kind of went away. Make sense? Okay. So let's expand this, this kinetic energy out. I'm calling that kinetic energy T. So if I look at each of these terms, I say, all right, what do I have here? I've got u equals the shape functions times the nodal displacements. That's the same thing going to be true with accelerations. The accelerations are going to be the shape functions times the nodal accelerations. If I'm looking at virtual displacements, it's the same thing across the board. Remember that trick we did before where if I transpose a vector that's the result of a matrix times or A times B, and I transpose it, I got to flip the order, right, in order for the dimensions to make sense. So here's my original expression that it's the density times virtual displacements times my accelerations. This is delta D n transpose, and that is n times my accelerations. So how did I get from here to here? It's just plugging this stuff in. Then I go back to my original expression, take this, put it down there, take my original expression for stored strain energy. My external work has to equal 0. There's that. Does that make sense? All right. All right. So if I look at this expression and I say, all right, I've got a delta D here and a delta D here, I can factor the whole thing out. Now on the right-hand side, I've got a number 0. In order for the dimensions to be right, I factor that out. I have to have a 0 vector. So that's where that comes from. I say, well, I got a delta D transpose, cancel it out, then I'm left with this. Okay? So what do I have? I have a pile of junk times the displacements and a pile of junk times the accelerations. This should be familiar, right? B transpose CB integrated over the volume, that's the stiffness matrix. That's K. I propose to you that this term here, N transpose N times the density integrated over the volume, that's the mass matrix. Does that make sense? This isn't that difficult, I promise. Everybody good so far? Okay. Now, we've got this finite element system that we need to assess, and this is where the eigenvalue stuff comes into play, because we don't have just stiffness times displacement equals the forces, and we can just invert and that's it. We have to take a different approach. We say, well, all right, how do you solve a differential equation when it gets kind of complicated, when the form gets kind of tricky? You learn this in DiffEqs that there's two general approaches beyond the numerical techniques and all that stuff. You can actually just directly solve it, or you can make an assumption about what the solution should look like. Okay? Remember how you do characteristic equations? Remember that? How like your second derivative becomes r squared, your first derivative becomes r, your third derivative becomes r cubed, and you turn a differential equation into a polynomial. You solve for your roots. Remember, the real roots become e to the whatever. The imaginary roots become sines and cosines. Y'all remember that from DiffEq? You do that by assuming that your solution is exponential. Okay? That's how you do that. Well, here, we've been using trig functions for what, I mean, the solution for the single degree of freedom system was trigonometric in nature. Makes a lot of sense that a reasonable assumption for these problems is that the solution or the displacement should be trigonometric in nature. So why don't I make an assumption that it looks like this? Some nodal displacements times the sine. Okay? Now I've got that omega in there just from last time. We've got that natural frequency. And since I've got derivatives in here, I take the first derivative and the second derivative. What's the derivative of the sine? The cosine. What's the derivative of the cosine? Negative sine. Okay? So see how I get that? And we say, well, all right. Plugging them in. So I assume, okay, so k times d, that's where that d sine omega t comes from. D and then omega squared sine omega t. Factor out the sine. I can divide both sides by the sine, and I can say, all right, factor out the displacements, and I get this. Okay? There's really only two possible answers to that problem. The displacements are 0. But that would be trivial. Now, we could say that the term inside the parentheses is 0, but that would be trivial as well, no stiffness or no mass. The only way to get a non-trivial solution is to say that the determinant of this interior expression must equal 0. Hence, this is our eigenvalue problem. Bless you. So instead of having like A minus lambda times I, we're dealing with a stiffness minus omega squared times m, but it's the same process across the board. It's an eigenvalue problem like any other, okay? So now the only thing left is to actually go through and derive the mass matrices, okay? So let's start off with a two-noded bar, okay? Pretty simple, okay? Now we're going to assume constant density and that the bar has a constant area. So literally like just a solid bar, let's derive our mass matrix. So remember these? These are the shape functions for a bar, okay? This is n transpose. So if I do n transpose times n, I know you all love doing this on homework 4. I can see you're just jumping, raring to do it again, right? No, the jokes just are, they're falling flat, guys. I know it's good material. I'm kidding, I'm messing with you. All right, if I take n transpose times n, I get this. Everybody okay with that? Okay. Now if I take that and I then integrate, okay, let's walk through this. So I'm integrating over the volume, but I'm assuming constant area. So really, I just need to integrate this with respect to x. This n transpose times n, I'm integrating each of these terms, right? So if we take a look at like the bottom right one, I think it's pretty easy to follow. So I've got x squared over L squared. Integral of that's going to be x cubed over 3 L squared. Integrating from 0 to L, I plug in the 0, it ain't going to give me anything, so it's just L over 3. Make sense? So I can do the same thing across the board, and I get this. Now, if I look inside this box, see how the L factors out? Okay, look at this. If I have a bar, what is the area of a bar times its length? It's volume. What's volume times density? It's mass. So this term right here, little m, is the actual total mass of the bar. It's the density times the volume. So you'll see that's where I'm getting that. So if I look at this, 1/3, 1/6, 1/6, 1/3, that's my stiffness matrix. Now watch this. You agree that m is the total mass of the bar, right? What is 1/3 plus 1/6 plus 1/6 plus 1/3? You add all those terms up, what do you get? 1. What we're doing, this is the total mass matrix for the whole bar. We're not making up mass. This is all about determining how much mass is associated with each degree of freedom. They better all add up to be 1. Okay? Make sense? All right. So there's your mass matrix for a bar. Okay? So if we summarize that out, for a two-noded bar, here's my mass matrix, here's my stiffness matrix. Done. Simple stuff, right? Now, if you just conceptually, we can say, all right, let's continue that out for a -1 + 1 domain, and we can numerically integrate it, and da-da-da-da-da, so on and so forth. We can also do the same thing for beams, quadrilaterals, three-dimensional elements, what have you, okay? Let's take a look at this. I figured I would give you this. I'm actually going to zoom in a little bit because I want you all to see this. So this is the stiffness matrix for a beam. This is the mass matrix for a beam. Okay? Everybody okay with that? That's just after going through and doing all the derivations and what have you. Okay, so for a two-noded beam, there's your stiffness matrix and mass matrix. All right, we're not going to do this example this time. We're going to do it next time. We're going to take this beam, and using one finite element, we're going to determine what is its natural frequency. So if I took this beam and took a sledgehammer and went bam, and it vibrates, I want to know how often it vibrates. I want to know its natural frequency. One final note I will make. We are using the finite element formulation. Let me go here. And this is especially true for this bar. We're using a finite element formulation to derive a mass matrix. Those who get embroiled into structural dynamics will call this a consistent mass matrix. They call it a consistent mass matrix because we use the same N matrix and B matrix to derive the stiffness matrix that we do the mass matrix. There's also the potential of what we call a lumped mass matrix. In other words, literally saying that this is a half and this is a half, and it's 0 everywhere else. And there are theoretical reasons why you would do that. For instance, when we do a building analysis, we assume that each floor is one big lumped mass at the floor. Okay? So if you look at it, it's like a series of bar elements, or really more like beam elements, but there's this big lumped mass at each floor. So a lumped mass matrix might make more sense in a problem like that. For us, however, where we're trying to do it a little more consistent and a little bit more with a finite element approach, consistent mass matrices seem to make more sense from a derived standpoint. But it's your choice as the analyst what approach to use. And you can actually split the difference. You can say, well, how about, here's a consistent mass matrix, here's a lumped mass matrix, let's just take the average. That's actually a valid theory within the world of finite elements as well. It's all about what you're doing and why you're doing it. Make sense? All right, that's all I have for you all today. Next time we'll actually take this approach and calculate natural frequencies of beams using finite elements, and it's pretty straightforward. Everybody good? All right, that's all I got.